Hi everyone, this is exercise 6 from lecture 4, and here we're talking about a toolbox that's placed on an incline and the angle's increased until the toolbox begins to slide down. A few things of note here: an incline is short for an inclined plane. Inclined plane. Okay, a plane is a flat surface and an incline says it's at an angle. This you might know better as just being a ramp. Okay, so often it's one of our simple used machines. Instead of carrying things upstairs or anything like that, we might find it's much easier to have a smooth transition. So instead of, a set of stairs which you might move a fridge up or have to lift something up, we can replace that with a ramp that we can simply slide things and push things up instead. Okay, in this situation, our ramp angle is 40 degrees. Just a bit of a story about what happens here. This is a simplified problem. What would happen is we'd start with the toolbox on roughly flat ground. It should be a straight line. As we then tilt this further up, our 14 kilograms. Our 14 kilograms. As we tilt up our 14 kilogram toolbox, it will start to slide. Now, our static friction coefficient is always or almost always larger than our kinetic coefficient of friction. So as this starts moving from being stationary, there is a less resistance to movement, and it would actually accelerate down the ramp if we left it at the same angle from when it started moving. So they would actually adjust the ramp slightly in this situation to account for the different size of kinetic friction versus static friction. But conveniently, this problem is nice and simple, and it just says calculate the coefficient of friction at 40 degrees is what this breaks down to. So let's draw our situation here. I'm going to draw it nice and large because we've got a few things going on in this one. Okay, our angle has been given to us. It's 40 degrees. Our toolbox will sit somewhere on it. We'll do that here. 14 kilograms. And it will have a weight force. And that is the force due to weight, which is not going to fit there. I'll write it on this side. No, I'll write it underneath. Force due to weight, which is its mass times its acceleration, which is 14 times 9.81. Let's put our units in there. Kilograms times 9.81. I know at the moment putting the units in there seems a bit unnecessary, but in later parts of this course and in later units, you'll be given things like centimeters, and it will have an acceleration in bizarre units, and you'll want to make sure that it is in a certain unit before you can convert the units. Before we go from kilogram meters per second squared into newtons, if it's not in kilograms or the acceleration isn't in meters per second squared, you can't say it's equal to a certain number of newtons until you do your unit conversions. So keeping the units with it is a good idea from just the start of solving these problems. We get 14 times 9.81, which is 137.34 kilogram meters per second squared, which is 137.34 newtons. Now, this force here, our force due to weight, can be broken down into a force that is perpendicular to this ramp and a force which will accelerate it down the ramp. So one of the forces here is pushing onto the ramp, and also one of the components of this force is pushing down, and the other component is sort of accelerating it down the ramp. So this one here is providing a force down the ramp. It's parallel to the ramp. To make our calculations easier, we're going to redefine where x and y points. Okay, I'm going to say that our y-axis, if I can keep it straight, our y-axis is going to be up, and our x-axis is going to be down the ramp, which is different to how we usually have it. Okay, and I'm going to show you here how my normal table looks. It'll look the same, but we're going to measure the angle slightly differently. It's going to be from positive x towards the y-axis, and that's going to be the direction that we're going to follow. You've probably heard me hinting that in class, saying it's not always x anti-clockwise, it's x anti-clockwise in our normal situation, but when our x and y have moved, then I'm going to measure from the x-axis towards the y-axis, which is how we measure in the normal situation, but here it's going to be clockwise instead. Our 40 degrees is, now this is where it gets a bit messy. You could remember where it goes with in there due to parallel lines. I always forget. So I'm going to draw this on here. I know this is just a movement up here of 40 degrees. Okay, if that's 40 in there, therefore this angle in here is the remainder part of 50, which means this part on the opposite side of these two dark blue lines is also 50. And that means, where's the last one? If it's 50 coming down here, so that's 50 in there. And our last part must be 40 in here, which is a bit tight. Effectively, I'll just redraw that very quickly here. We've got our force due to weight in the what would be the negative y direction, but it's our y value here. Sorry, this one is at 40 degrees here. This will be our force due to weight. Our force due to weight in the y direction is 40 degrees away from our force there. And if we're measuring from the x-axis, I'll come back to that one in a minute. And our other one, we've got a 90-degree angle here, because this is our force due to weight in the x direction, is at 50 degrees here. To be, where is that needed? I'll come back and I'll find that one in a minute. So, our table will have our x component, our y component. Oops, I haven't drawn on my friction force. If it's going to slide down the ramp and the velocity is down the ramp, then my friction force is going to be up the ramp. It's going to be opposing the velocity. And what we haven't drawn on there, if there's a force going down, remember this is a constant velocity, which means there is no acceleration, and Newton's first law says if there's no change in it, then the forces must be balanced. The sum of the forces must equal to 0. And you'd write due to constant velocity, or due to equilibrium, or since there is no acceleration, the forces must be equal to 0, or again, just something that shows that you understand why in this certain situation the sum of the forces should be equal to 0. Table down here. So we have our weight force. The first one we have to deal with is the hardest one to see. Our weight force is equal to 137.3 0.34, and we have weight force. This will still be cos of the angle, weight force sine of the angle. 137.34 cos of. Now, this is the x component, which, where are we? From the x-axis, actually let's zoom in. Can I zoom in? There we go. And we will, 1, 2, 3. Let's see if I can write really small. So this was 50 degrees in here. It's a bit blurry because my software isn't set up to write this small usually. And in here we had 40 degrees. Okay, and this is why I'm starting to try and encourage you to make your diagrams nice and large, because they do get a bit squashed eventually. We could of course say that the 40 degrees is in here. We could actually fit it in there. We'll do that instead. Okay, between the x-axis and the negative y-axis there should be 50 degrees, which is why this is 50 plus 40. And I just worked that out because 40 degrees was here, so 40 degrees should have been there. 50 was to that line, opposing the opposite angle is the same size, so if we go diagonally across, 50 degrees is here, and because we can see that this is a flat line, 50's there, 40's on that side, and this is saying, which angle's that? Corresponding angles. It's in the same spot along one line this way and two parallel lines up there. So, this one, no, that one. What have I pressed? Cancel. So, why I was doing this is because I want to know the angle of our weight force, the one that is down here. Running out of colours. So from our x-axis towards our y-axis, that is 90 degrees. If I went all the way around to my negative x-axis, that is 180 degrees. If I keep going around to the negative y-axis, that is 270 degrees, and I need to add this 40 degrees in here. So my weight force from my positive x-axis is 270 equals 270 plus 40 degrees, which will be 310 degrees. And that makes sense because the leftover part between the x-axis and that force is 50, so it could have also said it's equal to negative 50. A bit of a hassle. You can just, whoop, wrong one. That looks like my normal size. You could memorize when you have an inclined plane where the angle is, or if you know your angles in parallel lines better than me, you can just use the rules that you know. Zoom out to about there. But that was a bit of a detour, and we came up with the answer being, oops, wrong spot. The answer is 310. So we're going to say cos of 310. And same angle, same size, just sine instead. 137.34 sine of 310 degrees. And therefore our x component, the weight force, the x component is equal to, the x component of our weight force is equal to 137.34 cos of 310 is equal to 82.28 newtons, and the y component of our weight force is equal to minus, I won't do that minus again, 105.21 newtons. Which makes sense, double check these signs. 82 newtons in the positive x direction, which is down the ramp, and I should expect that we go along this path and then we go down away from positive y, so I should get a negative y. Makes sense. Our next one that we're going to put in there is our, oh sorry, I never drew on that normal force, did I? I think I talked about it, but I never drew it on there. Our normal force, we will just write it on here. Fn cos of theta. Just wondering if that's a bit thick, but we'll come down one size. And Fn sine of theta. Okay, Fn we don't know the size of, so it's Fn cos of, from the x-axis going out towards y, which will be 90, 180, 270. Oh, sorry. Let's look at that again. Draw our axes on here. My y is in the positive direction. My x is this way, and it's actually 90 degrees from positive x around to where this FW is pointing. So this should be 90 degrees. And then Fn sine of 90 degrees. Cos of 90 should be 0, which it is, which means that Fn in the x direction is 0. Fn sine of 90 is 1. In the y direction is just Fn. Yeah, let's just move down slightly. We'll try and keep that on there. What else have we got? We've done the weight force, we've done Fn, we're left with our friction force. Ff, our friction force, times cos of theta, friction force times sine of theta. We don't know what this is. Logically, it should be the x component of our weight force. But we'll just go through the sums, because sometimes you'll have an extra rope on here or something adding to it or subtracting to it, which will cause that to be something else. It's our friction force. Cos of, get yourself a small little axis. We've got positive y up here. Positive x was down the ramp. Therefore, this is 90, 180 degrees from positive x through the y axis. Goes that way. So this will be 180 degrees, and Ff sine of 180 degrees. Cos of 180 is minus 1, I believe. Where are we? Cos of 180 is minus 1. So F in the x direction is equal to minus the size of the friction force, because it's minus, because it's in the negative x direction. And FF in the y direction, sine of 180 is equal to 0. Sine 180 check it on your calculator, equals 0 newtons. Okay, that's what we've got there. And remember, we've said that our sum of our f's should be 0. So this is your total category. The sum of the forces in the x direction should be 0. The sum of the forces in the y direction should be 0. So we have 82.28 plus 0 plus our minus friction force equals 0. And if we if we add our friction force to both sides, 82.28 equals our friction force. And in the y direction, we have minus 105.21 plus our normal force plus 0 equals 0. So I know I've just put in 0 here, but I see three possible y components to add, so I make sure I have 3 things that I've written down here. It's again just one of the patterns I've got into the habit of doing, so it's a self-check way to make sure that I've added this, 1, 2, 3, yep, all good to go. Here I'm going to add 105 to both sides, which will get rid of off this side and put it on the other side. Fn is equal to 105 because I'm adding it to both sides, 0.21 newtons. I forgot to put in newtons here. Okay, now we know our friction force and we know our normal force. The question was asking, calculate the coefficient of friction. So what I do with any of these problems is to have an idea where you want to go and then do all of your working out and then go back and check, have you gone through and answered what the question has asked? Or have you just found out lots of interesting bits of information but not quite gotten to what the question is asking? It says calculate the coefficient of friction. So like the last question, we're going to use these two values in our formula from our formula sheet, saying the friction force is equal to the coefficient of, this will be kinetic friction because it's moving in the question, times our normal force. Now, my x and y direction happen to give me positive values here. So our friction force and our normal force were positive values. In the case that I'd defined x in the other direction, I would have had a negative friction force. Just thinking about that. Oh no. It wouldn't have actually, with this method, wouldn't have been. Because that would have been a negative number, that would have been a positive number. It still would have given me a positive number here. In the case you've made a mistake, and these numbers are, possibly this one could have been negative, and one of these is negative and one of these is positive, write a statement saying I'm ignoring the sign in this equation because I know the coefficient of friction must be positive. And so you know this must be positive. There might be an error in either Fn or Ff, the way you calculated it. Double check your vector diagram and your calculations, but if you can't spot it, just say this must be positive, therefore I'm ignoring the sign on Fn and Ff to make sure that this is a positive number. Working through, we divide both sides by Fn, same as the last problem, divided by Fn equals mu k, our friction force, which is 105.21 over 82.28. Let's try that the other way around. Why? Because that was going to, my friction force was bigger than my normal force, and in almost any circumstance that's not true. I think in some very rare physics experiments it does happen, but that's using esoteric materials, ones that we don't normally deal with. 82.28 over 105. Fn is 105. 05.21 is equal to... Now, if I include my units here, my newtons over newtons are going to cancel out, and I'm not going to have any units here because the friction coefficient does not have any units. And when I calculate this, I get 82.28, whoops, 82.28 divided by 105.21, and I get 0.78 as my friction coefficient. And on the whole, if we jump back up here, we're looking at things like two significant figures, possibly two significant figures, and my answer, even though I've written these down to a few more, 2 decimal places is also a reasonable thing to round to. Our friction coefficient at 2 decimal places or 2 significant figures is a reasonable thing to round to. You wouldn't want to have lots of decimal places off here because we didn't measure anything that accurately. So that's our answer. We would say UK was found to be or our friction coefficient 0.78. And there we go. Thanks for listening.